In the second video for section 11.1, we're going to talk about just general curves in space. Our last video ended with one particular type of curve, which is a line in space. But if our component functions for a vector valued function are not all linear equations, we could have some curve in any or all three of the x, y, and z directions. These could be difficult to draw in 3 dimensions, so we are going to introduce it just in 2 dimensions, and then we can possibly use the help of some sort of computer software to see what's going on with some 3-dimensional curves. So a line is a curve in space. Usually you think curve and you think it needs to be bendy, and that's not always true. But a line is our most basic example of a curve in space. For other types of curves, we would calculate the domain exactly the same, and we would typically already be given these vector valued functions. We wouldn't have to generate them ourselves the same way that we can generate a line in space. But mostly what we're interested in is seeing what exactly these curves look like if we're given a vector valued function. And then we're also going to introduce something called orientation. So to graph these curves, you have a couple of options. What I typically do is I like to break my vector valued function into individual parametric equations. And then we have equations individually for what's going on in the x, y, and z direction, and those values can also represent specific points that our curve is passing through. You also have the option, if you're working in 2 dimensions, to try and figure out what the equivalent 2-dimensional equation is in terms of x and y. So we'll talk about both of these. So to get this started, I'm going to go through an example to show you how we can do this with parametric equations. We're going to try to sketch a graph of r of t equals 3 cosine ti plus sine t j. It's much easier to graph the 2 dimensionals, and like I said, if we want to do 3-dimensional curves, we might want to use some sort of specific math computer software to help us with that. So this vector valued function can be written as parametric equations using x of t equals 3 cosine t and y of t equals sine t. So t is the independent variable, which we get to choose. And when we plug that t value in, it's going to give us back a value for x and for y. So I'm just going to create a little chart, and I'm going to plug in values for t. Sometimes you've got to carefully pick those values so that they make sense in your particular set of parametric equations, and that they generate points that are easy to plot. So since our parametric equations involve trigonometry, I'm going to be using common angle measurements for t. So I'm going to start at t equals 0. We're not required to start at t equals 0. We are allowed to use negative values for t. In application problems, t usually represents time. So in application problems, usually time will start at 0. But if we're not working with an application problem, really we can use negative values as well, and it would be fine. But if we plug in 0 for t into our x and y equations, we get 3 cosine of 0, which is 3, and we get sine of 0, which is 0. So another pretty easy value to plug into the trig would be pi over 2. Our equations will have nice whole number answers if we do that. If we try to just plug in 0, 1, 2, 3, 4, 5, we're going to get some really weird decimals out of the sine and cosine functions there that we have. But at pi over 2, 3 cosine of pi over 2 is 0, and sine of pi over 2 is 1. So I'm just going to work here with multiples of pi over 2. 3 cosine of pi is negative 3, and sine of pi is 0. 3 cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is negative 1. 3 cosine of 2 pi is 3, and sine of 2 pi is 0. So what we have here is some points that we can plot. We don't plot the t-value. There's not a t-axis. We're trying to plot this in the xy plane. So the first point that we generated was the point 3, 0. That is our starting point for when t equals 0. And you may even see the t-value labeled there. And then we did pi over 2 and we got the point 0, 1. And then 3 pi over 2, oh, excuse me, pi, we got negative 3, 0. 3 pi over 2, we got 0, negative 1. And if you remember anything about trigonometry, you will remember that we're just going to keep repeating these same values over and over and over again. Let me move that t label. So when we plugged in 2 pi, we were back to the 3, 0 point that we got when t equal to 0. So we're going to connect these. And we're getting an ellipse when we graph, or when we sketch our curve. Now, all vector-valued functions always have something called an orientation. And the orientation, because this is a vector, our vector-valued functions are technically vectors, which means they're going to have a direction associated with them. So the orientation is just the direction of increasing values of t. And we indicate that on our curve with just some little arrowheads. So if I just gave you the ellipse, we wouldn't know really where to start or what direction to go around that ellipse. So by including our little arrowheads, we're going to indicate which direction these points are moving in. So we started at t equals 0, and then we moved to t equals pi over 2. That took us to from 3, 0 to 0, 1. So we're moving in this direction. And then we went from t equals pi over 2 to t equals pi. That took us from 0, 1 to negative 3, 0. So it looks like we're going around this ellipse counterclockwise. So we just put those little arrowheads in there to indicate the orientation of this curve. And it's the direction where our t's are getting larger. Plotting points is not always the best way to come up with your curve, because if we don't use appropriate points for t, we might not generate a list of points that really give us all the characteristics of our curve. So another option is to change your parametric equations back into an equation that just involve x and y. For this particular example, we're going to do something special because it's got trigonometry. But I'm going to give you just a general idea of how we do this. You're going to solve one of your parametric equations for t, and then use it to replace the t in the other parametric equation. Then we'll have eliminated the t and we'll have just one equation with x's and y's in it. The example we just did requires a little bit of extra instructions because it has sine and cosine. So it would not be ideal to solve one of these equations for t because we would have to do inverse trigonometry in order to do that, which is fine. It's perfectly legal, but it's not the best way to visualize and get a good understanding just from the xy equation of what this graph is. So if you've got trig, you really want to use a trig identity. So if your parametric equations contain trigonometry, we're going to try to match them up with some sort of trig identity. And which trig identity you use is dependent upon which trig functions you have in your parametric equations. We've got sine and cosine. So the one that pops into my mind with sine and cosine is the Pythagorean theorem sine squared, and really what we use for the angle doesn't really matter. I'm just going to say t. Sine squared t, well, maybe I shouldn't use t because we got it in our other equation. Let me just say sine squared theta plus cosine squared theta equals 1. This equation is going to allow me to take both of my parametric equations and put them into just one equation. The way that we get them in there is we're going to solve these equations for sine and cosine. So right now, we've got x of t equals 3 sine, is it sine? X is cosine. X of t is 3 cosine t. Y of t equals just sine t. Now you might want to drop the function notation when you do this and just write this as x equals 3 cosine t. And now to solve for cosine t, we just have to divide the 3 over. So cosine of t is x over 3. And then when we drop the function notation, we have y equals sine of t. So sine of t is equal to y. So we're allowed to replace sine and cosine in that trig identity with what we have figured out they are equal to in terms of x and y. So sine of t is equal to y, which means I'm going to have y squared, because the trig identity says to square it. And then cosine is equal to x over 3. So I'm going to have x over 3 squared equals 1. In a more recognizable format for this, x squared over 9, if we square both those pieces, plus y squared equals 1. You may have learned this at some point, but this is the equation for an ellipse. So it's a lot easier if you're familiar with the different xy equations and the graphs they represent. to do this in XY format by eliminating your parameter, is what it's called. T is a parameter. It's not actually a variable that we plot, but it helps us to determine the coordinates that we're going to plot. It helps us to move along our curve in the correct increments in both directions, x and y. So we could easily draw the graph of x squared over 9 plus y squared equals 1 if we recognize that's an ellipse and we remember how to do that. If there's no trig in the problem, it's even easier. So we're going to eliminate the parameter. That means we want to get rid of the t. We just want it in terms of x and y. Eliminate the parameter to determine an equivalent xy equation. For r of t equals the square root of t plus 2 and t minus 4. So no trig in this one. We can go back to just those basic instructions that say we're going to solve one of the parametric equations for t, and then we're going to use it to replace the t in the other parametric equation. We've got two equations with t, and a lot of times it's completely up to us which one we solve for t and then use to replace in the other. One thing you do want to avoid when you're solving for t is having to take square roots, because if you remember from algebra, when you take a square root, you've got to put a plus or minus in front of it, which means we're actually generating two curves. If we can avoid taking square roots, that would be optimal. So on this one, there is no squares that we would have to take a square root in order to solve. Whenever possible, though, we do like our y written as a function of x. So if it makes sense and it isn't too difficult to solve the x equation for t, when we then plug it into the y equation, we'll be done. We'll have y as a function of x. And usually the shape of the curve is much more recognizable when it's written in that format. So I'm going to solve my x equation for t. I've got x equals the square root of t plus 2. So the first step to start solving for the t is I need to square both sides. And that'll pull the t out of the square root. So now we've got x squared equals t plus 2. The next thing I need to do is I need to subtract that 2 over to the other side, because I'm trying to solve one equation for t. So what we get here is that t equals x squared minus 2. And then we can use this to replace the t in the other equation. So now we have y equals x squared minus 2 minus 4. All I did is I replaced the t with x squared minus 2. And we could simplify this a little bit. This is y equals x squared minus 6. We need to be careful. There is going to be a domain restriction on this. Remember, we can't take the square root of negative numbers. So if you look at what the domain for this function is, x of t equals square root of t plus 2, remember that t must be greater than or equal to negative 2. The smallest value I'll ever get back from a square root is 0. So x ends up as greater than or equal to 0. So we add a domain restriction. You might recognize that y equals x squared minus 6 is just a parabola, but based on the parametric equations that these started as, we're never going to get any negative x values back. So our domain restriction is x greater than or equal to 0. And when we look at this graph, this is a parabola with its vertex at negative 6, 0. this is the entire graph. But remember, we can't generate those negative x values because a square root will always get a positive answer. So we're actually only going to use part of this graph. And we're only using the part when x is positive. Which is to the right of our y-axis. We could also figure out the orientation, and that's probably easiest from your parametric equations. If we were to plug in t equals, and then pick numbers that make sense, t equals 2, that way I get a nice perfect square under my square root. I get the square root of 4, and then negative 2. If I plug in t equals 7, I get the square root of 9, which is 3, and I get 7 minus 4, which is 3. So if we just kind of eyeball where this is on the graph, here's 2, negative 2, not really, but, and then 3, 3. Oh, this is way off. Here's 2, negative 2. And here's 3, 3. We went from this point to this point, so that helps us with the orientation of the graph. Now we're going to wrap up this section with a quick little discussion on limits and continuity. Because both of these relate to the sketching of our curve. So we've learned that vectors can be added, subtracted, and we can do scalar multiples very easily. And we spent our first few sections of this chapter showing how to do that algebraically and also graphically. If R is a vector-valued function, such that R of t equals x of ti plus y of tj plus z of tk, then the limit as t approaches some value for R of t, we can really break this up into 3 different limit problems. When we did addition, we broke it up into 3 different addition problems. We added component-wise. We added all of the x components, added all of the y components, added all of the z components. So we've already established this pattern of when our vector is in component form, it can be broken up like into 3 little mini problems. That's also how we did domain. We needed domain of each of those individual component functions. So if I want the limit of a vector-valued function, we really could just treat this as the limit of the x portion plus the limit of the y portion plus the limit of the z portion. Since all of these component functions might be very different and require different limit techniques, it's going to be much more convenient to think of this as 3 separate limit problems. That way we're only dealing with one function inside of each limit. As we learn in Calculus 1, always try direct substitution first. If direct substitution doesn't work, just as a quick review, direct substitution means we're just going to take that a value and plug it in for t and see if we can get an answer. And then if direct substitution doesn't work, we might have to apply some of our limit techniques. There's some algebra techniques, there's L'Hopital's rule, and a few different things we can do. So a couple of quick examples, and we'll talk about how this relates to continuity, and then we'll be all done with the section. We want to find the limit as t approaches 4 for r of t. If r of t is t squared minus 2, 2t plus 1, and e to the t minus 4. So we're going to individually see if we can just plug 4 in for the t's and get an answer. So when we try that, we're going to get 4 squared minus 2, which is 14. 2 times 4 plus 1, which is 9. And then e to the 4 minus 4, which is e to the 0, which is 1. So direct substitution works beautifully on this. And that should always be the first thing you try because it's the easiest thing to do. So we're done. That's our answer. Oops, don't want to use x's, want to use t's. So we've got t over t minus 1i plus t over sine t j, and then cosine t k. So I'm purposely writing my vector here in our alternate format, just so you know that these two formats are completely interchangeable and you're going to see problems with vectors possibly written in either way, so we need to be comfortable with both formats. If we try direct substitution here, so I'm going to write this in red, I'm not positive this is going to be our answer. If we plug in t equals 0, we get 0 over negative 1. 0 divided by negative 1 is 0. So that's fine. When we plug 0 into the y component, we get 0 over sine of 0. We get 0 over 0, which is a problem. That is called indeterminate form. When we plug 0 into our z component, cosine of 0 is equal to 1. So two of these pieces are perfectly fine. It's only the y component that we need to fix, technically. We need to do some more work on. So the fact that we're allowed to break this limit up into individual pieces allows us to stop with the x component and the z component. Those are done. Those are definitely going to be the x component answer and the z component answer. But we've got further work to do on the y component. We need the limit as t approaches 0 of t over sine t. That gave us a problem. We got 0 over 0, which is indeterminate form. Well, there's no way to algebraically fix that because we've got trig in there, but you can apply L'Hopital's rule. And L'Hopital's rule says anytime you get an indeterminate form, you take the derivative of each piece, and then you try direct substitution again. So the derivative for t is 1. The derivative for sine t is cosine t. Now if I plug in 0, I get 1 over cosine of 0, which is 1. And 1 over 1 is equal to 1. So perfect. Just one little application of L'Hopital's, and we've got our final answer. So we've got 0, 1, 1. So where this links into continuity, first let me remind you exactly what continuity is. So just kind of a geometric description or graphical description. Anytime you can draw an entire curve from start to finish without lifting your pencil, you're dealing with a continuous function. So think back to algebra, or maybe calculus 1, of some different characteristics of our function that might require us to lift our pencil. What this means is our graph has no holes in it. It's got no asymptotes in it. It also has no jumps, and jumps we sometimes see with piecewise function. When we transition away from one of the pieces and then start working on the second piece, if those two pieces don't match up at the same y value, then there's going to be a big old jump in our graph. And we would have to lift our pencil and physically move our pencil to the new location to continue drawing. And that means it's not continuous. So there's a way for us to decide if our graph is continuous just based on limits. So r of t is a continuous vector-valued function, and its curve is also continuous if, let me say at a certain spot. Let's just say at t equals a. If three things are true, all three of these have to be true. The first one is that r of a exists. You can just plug a in for the t's and get an answer. We also need the limit as t approaches a for r of t to exist. Both of the limit examples we just did, both of them existed. We were able to come up with an answer to the limit for both of them. The third case is usually where this fails if it's going to, and that is that the limit as t approaches a for r of t is equal to r of a. We want the answer that we get for the limit to be exactly the same as what we would get if we just plugged a directly into the vector-valued function. And really what this means is that the limit can be evaluated with direct substitution. If you have to use any special math tricks like algebra simplification or L'Hopital's, that means it's not continuous. If we can get our answer for the limit with just direct substitution, that means the limit exists. So what that means for our last two examples, the first one we did, where the limit as t approaches 4 for our r of t, we were very easily able to get the answer 1491 just by plugging 4 in, and we had to do no special math tricks, no algebra simplification, no L'Hopital's. That means this one is continuous. However, when we did b, the limit as t approaches 0 for r of t, we were able to get answers easily with direct substitution for the x component and the z component, but we had to apply a special rule here in order to get the answer for the y component, which means direct substitution did not work on the y component, which means this vector valued function and its curve are not continuous. So from the examples above, A is continuous. We got our answer with direct substitution, no problems. B was not continuous. And that's because we had to use L'Hopital's.